This is a sample problem.
We're going to talk about the technical
sample
meaning of
calculation.
power.
We're
I
going
don't
to find
mean
the work
power
is
over
right.
This is the OpsSARS video for section 4,
the power
geometry.
is an amount of work.
Now, one thing that some people get confused about is the difference between surface area and cross-sectional area.
For
So,
example,
as an example
I
of that, I
might
thought I would
heavy
look
lift
at a cylinder.
and in 20 seconds, I might
You might think of it as a can,
Given some information about
surface of a can.
30,500
joules.
Let's compare the
And my average
surface
power
area with the
during
cross-sectional
that
area.
interval
So
of
first of all, if I look at the surface area of this object, it actually has three
Now,
surfaces.
there may be bursts of lifting
So
in there.
what I'm going to do is
kind of lack the
add the
force
area
average
of all three surfaces together.
Acceleration, how to use this was 0.26
There are two ends,
and
and then there's the curved part.
Work done by
So the area of each end is going to be pi r squared, which is the area of a circle.
before they hit each other.
Well, that's
Then I need to add to that the area of
I
the curved
could
part.
be talking about
The way you can think of that is to think of
R for short.
the circumference of a circle,
power.
and then stretching
If
that
I'm talking about the
circumference
power
down the
output
length
of a car,
of the
I'm
cylinder.
talking about at any
So the
given
circumference of a
moment,
circle is 2 pi r.
the car's power
And
right
you
now
multiply
is
that by the length of the
Because
cylinder.
the acceleration is constant.
Now what I want to do is simplify this as much as possible. I'll give the surface area the symbol A.
You're talking about instantaneous
If
power.
I add the
You want to know the
two
rate
areas of the ends together, that's 2 pi r
just
squared.
in that
There's
instance.
another hit.
For example,
And then, to make this easiest to use, I'm going to factor all the common terms out.
the distance they travel.
So here's the final
And
expression.
that's where this other
2 times
information
pi times the radius,
to the center.
and then what's left is the radius plus the length.
I wanted the
to the right.
power.
So that would be the area of the surface of the cylinder.
of that
And that area is
Force from
the
the
boundary
acceleration
between the object, the
35
cylinder, and this environment.
Negative.
Now if I take that
the
cylinder and slice through it, then
from that
one more thing.
I would be measuring the cross-sectional area.
Calculate
So imagine that this is
The work I'm doing
I don't know.
could be because I'm applying a force to something.
What I find,
Let's make it a
just
block.
before they
loaf
hit
of
each other,
bologna.
they're traveling.
And I take a knife,
Let's say I'm
and I
pulling
cut
on
through
the
it.
block with a
Let's say I
certain
cut through it this way.
force at a
Chop right down through the middle.
And
when I do that, I get
the work I do
our
else and
smaller
I
cylinders.
pull the
Any
block
way you
to
wish
some
to
distance
show it,
called X.
they're going awfully fast, and you're about
And
to
so
go
the cross-sectional area would be the
F.
new areas that's
Well, it's
exposed.
not my full
Next,
F.
go after
Now
the
really,
mass.
in this
I'm
case, there are
pulling.
2 of
I have
those.
full
I'm not going
weight.
to double count
Now
them. I'm
they
just
go
going to
after
count
the
them
work
once.
I could do
in
better.
So
by
the
going
cross-sectional
directly
area,
right
if
then
I
millimeters.
slice
We're
it
going to be
displacement, but I'm going to stick
perpendicular
with
to
my
the length,
foolishness.
Right down each
then
other.
that cross-sectional area
Here's the
is
point.
just the area of a
happens
circle.
to be along the
And again, I'm not going to double
This is
count.
the component that
I'm not
actually
going to
Zero
count
in
both
the
of those
initial
circles, just
position.
one of them.
1/2 MV
Like
squared.
the
The cross-sectional area would be
the
pi r
work
squared.
I do
You can
is
see that's different than the
my
surface
force
area.
component
Okay, we
So I use
multiplied
the
by
symbol for
the
that.
displacement.
Unfortunately, a lot of times we use the same symbol
Well,
A
power
just for area. So you have to know from the context what the symbol is standing for, surface area or
With that
cross-sectional area.
displacement, the spring does.
Now what would happen if we took the same
Negative force
People
is
zero
not changing
flying
slab
tree
of
or
bologna.
only the distance
instead of,
that's changing with
We've got the
time.
package
cutting
all the
it
way over there at
perpendicular to
17
length.
millimeters.
Angle.
And now we're going to
So when I
move
cut
it
it across the
to
middle like
the
this.
other side
Right,
of the
that's
0 mark
front stuff
to
down,
x equal
and
So if
negative
you
12.
cut through it like that, let's say it's exactly through the middle.
Again, we want to know how much work
wait
what
a
you
little
would
bit longer,
get,
and I
the
lose
surface
the block
that
a little
would
bit
be
farther on
exposed,
the package
along
during
if I look
the
at it
this
from the top,
displacement.
Well,
would be a
the
rectangle
XT,
like
however,
this.
Well,
is
we're going to use the same
velocity.
formula.
Oops.
It's
So
going to be
power
work is equal
is
to
F
the work done by the spring is
cosine
going to be equal to
phi.
So
half
the cross-sectional area
K
depends on how you
X
slice
I
it,
squared
which way
minus
you
1/2
cut
K
the object.
X sub F
So
squared.
in this case,
trig
We're
functions
going to
we
put
get a
numbers in.
rectangle,
The initial
and
position
Oh,
this
and
time
look,
is
two
17.
sides
that's just
of
a
this
long
rectangle
way
is
of
the length
writing
of
out
the
a dot
cylinder.
product.
17
And
times
then
10
The
to the
dot
minus
product
5,
is
meters.
F
that's the diameter of the
The
circle,
final
which
position
is
is
the
going to
same
be
as
the
negative
force vector
12
dotted
millimeters
into the
Right.
velocity
Right.
vector R.
So in this
Minus
case,
sign will
really
of course
doesn't make a
disappear
difference
because
which
we're
way
in
you
this
squaring that
direction.
coordinate.
on a dot product.
the
What we get
cross-sectional
out is
area
positive
comes out to be
point
So
zero
this is another way
zero
that I
joules
could
multiplied by half.
write down
30
the
millimeters.
If I wanted to express that in terms of radius,
This is how much work
the
the spring
diameter
has done, and this time
twice
that
that,
work
yes.
is positive.
Now, let me
The
give you a
question here
cross-section
is,
area would be
why is it
2 times the
positive?
radius
Well,
times the
suppose
length.
I am
package
pulling
out
at angle
So it's important to
phi,
recognize
let's
the difference
make
between
the spring did
surface
negative
area and
work.
cross-sectional
We
area.
did
This will become
positive
very
work.
important
So
later
there's
on
the
when we
negative work.
start talking
and
about
How
phi
come the
is
spring
now
is doing
how
positive
energy
work?
moves from one place
Can
to
you
another
see
because
that
of the
I
temperature
will do-
difference.
Brought the package
I will have the
from
most
70
power
called heat.
to zero.
because
And
Did
the
a
amount of heat that
fairly
flows
large
angle in
amount
this
of
in various
positive
cases
work.
will
here
depend on
is
It
now
will
going
do
to be
one
a
of these kinds of
small
areas.
amount of negative
Now,
work.
So it's a good idea to
The
distinguish,
compression
in which
from
case
x
I get a
equals 0
cosine of
to
0, which is
negative
1.
12.
and I recommend
get
that you
the
go through the
greatest
same
power.
procedure for
A
other
large
shapes.
amount of positive
For
What do I
work.
get
example,
if
spheres
Negative work.
and
pull
cubes,
Overall,
at an angle
positive
shapes
amount
like
of
that.
work.
90
'cause
degrees?
that'll
And
be
that's
Blocks
it
useful
moving,
later
for
on.
this
sliding.
video.
So go
Somehow
ahead and
it
try
was
that
already
out,
made to slide, and now
and we'll
I'm
see you
pulling
later on.
upward. Not enough to lift the block. It's still sliding across the floor. Can you see that this is, shall we coin a phrase, stupid? Because if I put in 90 degrees right there, cosine of 90 is 0. I'm pulling up for nothing. The power that I'm using to move the block is 0. I may be straining muscles, but I'm not going to be making the block go faster or slower. Now, for 0 degrees, I had the most power I could get with the given amount of force, and so I would be making the block go faster and faster and faster. I'm adding energy to the block. I'm adding nothing, no energy to the block here. And one more case, block's still sliding to the right, but I'm pulling to the left. So the angle between the displacement vector, still x to the right, and the f vector, well, that's going to be 180 degrees. Can you see that when I put this in, I get -1? I will be removing energy from the block. I'll be making it go slower and slower. The power that I'm applying to the block is now a negative number because I'm taking energy away. Let's do a little quick summary of ideas here. Power is the ratio of work to time. Average power, you're averaging the amount of work being done over a time interval, 30 seconds, an hour, a day, something like that. But you could be worried about the power at a given instant, instantaneous power. That's the rate at which work is being done just then. We can also write power, the instantaneous power, as the dot product of the applied force and the velocity of the object just then. And this is the way we can expand a dot product. Magnitude of F, magnitude of V, cosine of the angle between those two vectors and the dot product. And that's it for this little video.